Okay, so they want the dot product, right? They say, use the dot product to determine if they're orthogonal. That's right. What's orthogonal mean? 90 degrees. Just a fancy word for perpendicular, right? So I want to use the dot product to find if they are orthogonal. So what should the dot product, how does the dot product tell you when two vectors are orthogonal? How do you know? Yeah, good memory. Good memory. You didn't think about anything else all weekend, sounds like. All right. So yeah, so they're orthogonal when, whoops, I'm kind of scribbling there. When V dot W equals 0. Yeah, that's the deal. So that was a theorem I gave you. I think it was like right at the end of class on Wednesday. So it was like the last thing we did, I think. So when the dot product is 0, it turns out they're orthogonal. And that's because, remember we had that formula with the cosine of the angle? Remember that? You don't need to, here's the y. Real quick, you don't need this, but remember we had that formula. The cosine of the angle is for two vectors is their dot, the angle between. Where so if you have two vectors, you have like, whoops, sorry, I'm not drawing very well here. If you have two, say you have a vector like this and a vector like that, call that V and W. The angle between them, theta, the angle between the two vectors, the cosine of that angle is V dot W over magnitude of V times magnitude of W. Remember that little formula? So that's how you find the angle between two vectors, is you dot product them divided by their magnitudes multiplied. That and the cosine of the angle between will be that. Okay, so what? Well, if they're perpendicular, say V's like this, is V here, and W's like that, they're 90 degrees orthogonal, then what does that mean? What is the cosine of 90 degrees? That means the angle between them would be 90 degrees, right, if they're orthogonal. And what's the cosine of 90? Remember from the unit circle? 90 degrees is straight up here. This is over 0, up 1, cosine 0. So this thing just equals 0. Remember that? So that's why this is true. Because if there's a 90 degree angle between them, then the cosine of 90 is 0. So what? Well, if this fraction is 0, how do you make a fraction 0? Top has to be 0. Has nothing to do with the bottom. There's no way the bottom being 0 can help. That makes it undefined, huh? So the top has to be 0. So long story short, if the angle between them is 90 degrees, if they're orthogonal, then the dot product, the top, has to be 0, doesn't it? So now we can use that. So you don't need to do all that. I'm just saying, just take the dot product really quick. So let's do it. So 2I dot 5. I don't know what's wrong with my pen today. Come on. 5I. So what's the dot product with 2I and 5I?
Would it be negative 5 or is it 5?
Oh, thank you. I lost the negative sign there. 2I dot negative 5I. It's just 2 times negative 5, huh? You just multiply the numbers. You drop the i's, don't you? And if there were j's, we drop those too. We just don't happen to have any j's. A weird one. It's just got i's. So 2 times negative 5, negative 10. It's not 0. So no, they're not orthogonal. That easy, huh? So all that cosine stuff was just the reason why. You don't have to do that. You just dot them. If it comes out 0, yes. If it comes out not 0, no. They're not orthogonal. Really, we could have known that question from the beginning without doing any dot product, huh? Did you think about what those vectors look like? What is the vector plus positive 2I? Remember what the I and the J are? I is the sideways, J is the up down. Remember that? They're like X and Y basically, huh? I and J. So 2I just goes 2 to the right, doesn't it? It's just that arrow going, there's the 2I vector, there's the V vector, and where's the W vector?
Backwards 5.
Back 5, 1, 2, 3, 4, 5, back. There's the W vector, it's back 5I. So are they perpendicular? Clearly not. They're 180 degrees, huh? They're not 90. So we could have done that too. Here's the problem. Can you do that? Can you start off by taking 5 times vector u? So So take vector u and multiply by 5. All right, so 5 times vector u, so I'll bring it over here, 5 times the minus 2i plus 2j dotted with, and then the other stuff is 3 times vector v, that'd be 3 times 3i minus j minus 4 times vector w, which is the minus 6j vector. We good there? So far, so good. Just kind of plug everything in. And can you work it out from there? Give you a second. Okay, so distribute. This will be minus 10i plus 10j, that vector, dotted with, and then the other side, distribute. 9i minus 3j, then the minus 4 plus 24j. And then we can simplify that one, how these two will combine. So we'll get 9i what? Plus 21j dotted with minus 10i plus 10j. We good? Good to there? And now, so we got the left side answer. So now we do the dot. How do you do the dot product? I with I, j with j, drop the i's and j's. Right? Just go the I times the I. It's like an easy FOIL, huh? Where you don't do the middle. Just I with I, j with j, drop the middle. So it's going to be what? Negative 10 times 9. What's that? Negative 90. And then 10. And I drop the I, notice. Just negative 90 straight. No more I. And then 10 times 21. 210. Drop the j's, huh? And then just finish that off. What is that? 120. There it is. Notice it's a number. So 2 vectors or 3 vectors and all dotted together comes out to be just a number. You know what they call that in the, I don't know if you noticed the title. Instead of just saying it's a number, they invent a really fancy word. I don't know why they always do this. It's called a scalar. It just sounds impressive. I don't know. It's just that's their way of saying it's a number. It's not a vector. The answer is just a number. The way you'll see it here, they'll say, find the specified scalar. And you might wonder, what do they mean number? Number or vector? They mean like, is it going to come out a number or is it going to come out a vector? It comes out a number. A scalar, they call it. Which just means a number. Not a vector. It's no longer ij, in other words. It's no longer a vector. Good? Questions? We good? All right, I'm going to move on. How about this? V and W. Now they're going to, here's the orthogonal thing again, but they're also throwing in the parallel idea. So they're saying, hey, can you take those 2 vectors and figure out, are they parallel, orthogonal, or neither, right? Are they in the same direction? Or are they perpendicular, orthogonal? Or are they like somewhere in between? Right? So let's try that. So number 10 here. V is 4i minus 5j. And W is 8i minus 10j. And they're saying V and W, are they orthogonal, means perpendicular, parallel, or neither? Right? So orthogonal would be like 90 degrees. Parallel would be headed the same direction. And neither would be like, not parallel and not 90 degrees either. Kind of just, So like with streets, a street corner, those are orthogonal at an intersection. And then parallel streets are those that go the same way. And then neither, that'd be like weird streets that kind of head off a little bit different directions, but not exactly 90 degrees. So.
Most of Fresno and in downtown.
Yeah, downtown, right, yes. All right, so try that one. So first off, how do we test if those two vectors are orthogonal? We have a different test for each one. So orthogonal, we just did it. That's dot product 0, right? If the dot product is 0, they're orthogonal. So I'm going to take v dot w equals 0. Does it? Does it equal 0? That's the question. So let's take vector v, 4i minus 5j dotted with vector w, 8i minus 10j, and that equals what? So I times I, j times j, drop the i's and j's. 32 minus 5 times minus 10 would be 32 plus 50. It's 82. It's not 0. So no, they're not orthogonal. So far, so good? These vectors are not 90 degrees with each other. They're not orthogonal. Now, how do we test for parallel? I haven't really given you a test for that yet. What do you think? How do we test if two vectors are headed in the same direction?
You look at it.
Yeah, you look at them. I like your answer. I agree with your answer. Basically, Kevin's right. Look at vector v and vector w. Do you notice anything about them? Yeah, one of them is twice as big as the other. So, if one vector is a number times the other, then they are parallel. So, in other words, if I can just erase this stuff up here, I'll do it up here. So yeah, the answer to this one is yeah, they're parallel. But let's see it. I want you to see, because just hearing some rule without a picture, I don't think is very helpful. So let me just show you on the picture. So just think about these vectors for a minute. Let's do vector v. What does he do? I'm going to put him at the origin. Starting from the origin, vector v is 4 to the right. Remember, i's right, left, j's up, down, x like x and y. So go right 4, down 5. Right? So there's vector v. Vector v. Right 4, down 5, isn't he? Vector v. Okay, now, let me put in vector w. What's he? He's right 8, 5, 6, 7, and putting it to origin again. 8, down 10. 5, 8, 6, 7, 8, 9, 10. Yeah, down 10. So in other words, he's right here. In other words, you get it? They're in the same direction because w is exactly v, just two of them. Right? So if one vector is just a number times the other, then that means they're headed in the same direction. One of them is just more of that. Get the idea? That's how you know they're parallel. If one of the vectors is a number times the other, then they're parallel.
Are the vectors always going to be from the origin?
Remember, what can we do? Remember the big lesson I shared that I was in calculus 2 and I was struggling with vectors and they were moving them around on me, and I said, "Can they do that?" And I went back and read the original definition. Vectors can move anywhere. Remember? And I did the Despicable Me, and he said, "I am vector. I am magnitude and direction. I'm not position," in other words. Yeah, vector's a good question. Vectors can be moved anywhere. So V is the same vector if you move it over. As long as it's right 4, down 5, it's the same vector. Yeah, it doesn't matter where they sit. So I just move them wherever I want for convenience. Yeah, so you can move it, right? It's still parallel if I put it over there, huh? Because it's still right 4, down 5. Yeah. So, yeah, vectors are just magnitude and direction, just like Despicable Me. Disney got it right. Is it Disney? Whoever that is. Universal. Okay. Well, they got it right. They did their math right. Vector is just magnitude and direction, just how long and which heading. It has nothing to do with position. You can move vectors wherever you want. Take physics, especially physics. You'll see that's what they do all the time. They'll have, somebody's pushing on a wall or a chair aside, and they'll say, this is the force vector here, and this is the vector there, and da-da-da-da-da. You put these vectors And I always tell you, I'm doing physics with my daughter right now. Just this weekend, we had things that were rotating, and we moved vectors here, there, and everywhere. So vectors can move. Good question. So yeah, so there's the two tests: orthogonal, dot product 0, parallel. One vector is just a number times the other vector. Then, and how they would write that, sorry, I knew there's one thing I wanted to tell you. How they would write that officially in math lingo, let me start introducing a little more official. They don't always write nice, clean sentences. They use math lingo, which would go like this. Vector V is K times vector W. This says what I'm saying here in words. Do you see it? What's the K? K is like any number. It's a vector V is any number times vector W. That's what this is saying. Just so you get used to that kind of lingo. When they write, they'll say they're parallel if V equals KW. And so you want to kind of start to speak their language, especially as you go up the line, especially if you have a professor that maybe doesn't break it down into English for you all the time, expects you to speak math a little bit more. That's math speak there. That means one vector is just a constant number times the other vector. That's how they do that. That kind of thing comes up a lot. It's not just for vectors. All kinds of things in math say one thing is a constant times the other. That means this. All right. Try. We'll do it. It's a 1-minute problem. Try those. Chanel has already solved it. It's a 10-second problem for her. Yes. Parallel, orthogonal, or neither. Okay, yeah. So if you dot them, it isn't going to work. If you do the dot product, it's going to be I times I and J times J. What's that? 12, and then minus 7 times 9, 63, whatever. I don't care what it is. It's not 0. Right? So they're not perpendicular. They're not 90 degrees. They're not orthogonal. So that one's a no. Are they parallel? No. Can you take this guy and multiply by a number and get that guy? Well, and how you can know for sure, you think, well, how do you know? Maybe there's a number we didn't think of. Well, the only way you're going to make the I work is multiplying by 3, huh? Right? If you multiplied that guy by 3, 3 times 2i, that'd make the I part work, but that wouldn't make the J part work. 3 times 7 would be 21, not 9. So clearly there's no way. The only number that would make the I part work will not make the J part work. So there's no number that makes them both work. So no, they're not parallel. They are neither. That good? Was it no? Everybody okay with that last reasoning? No number could work. They're not just one number times the other. They're not just a number of times one is the other. All right. All right, try that one. Are they parallel, orthogonal, or neither? Give it a try. Any conclusions? Okay, let's try the first test for orthogonal. I times I. 2 times 8 is? 16. So I'm doing the dot product right now, right? I'm doing the dot. 2 times 8. Yeah, here, I'll just write it out. 2 times 8. I'm having trouble. What's wrong with the pen? Maybe I need to adjust this thing. 2 times 8. And then, come on, minus 7. 7 times 16 over 7. Okay, so that's 16. And then what happens when you multiply a whole number 7 times a fraction? Yeah, you put the whole number over 1, don't you?
And wouldn't you distribute the negative?
And they cancel. So it's negative 16. And it's 0. So they are orthogonal. orthogonal. Does that make sense? The dot product comes out 0. Questions on that? That good? Ready for the word problems? You see it down there, the wagon. Here we go. A wagon is pulled along level ground by exerting a force of 40 pounds on a handle that makes an angle of 60 degrees with the horizontal. How much work is done in pulling the wagon 70 feet? So, what do they mean? Well, what's the actual question? What do they want from it? If the answer is 23, it's 23 what? Like, what do they want in the end? How much work? Yeah, did you notice that? How much work? What's work? I mean, we know what work is, but I mean, what's work in this math, physics kind of sense?
Pretty much how much pressure you got to put to move it a certain distance.
Yeah, it's force. Pressure's actually a little different. Pressure's force divided by area, a little different. But it's force over air distance. I'm going to start with the official definition. So here it is. So the official definition of work is force dot distance. See the dot product? That's why we're doing this word problem in the dot product section, because it's a natural application from physics to find work. So force, this is a force vector. And force is pounds in English units. It's newtons in metric, but we're not going to do metric. And distance is almost always going to be feet. So, but careful, this isn't just distance, it's a distance vector in feet. So it's a vector. They both have I and j, in other words. Maybe j is 0, but they both have an I and a j. They're both vectors. They're not scalars. No, those are not numbers. They're both vectors. So let's look at the problem. So going back then to the problem. The wagon is pulled along level ground. So to get the idea, I'm going to draw a picture, and that's always a challenge for me.
If it was in metric, would it be over meters?
If it was in metrics, this would be newtons, and this would be meters. And the work would be newton meters, also known as joules. So we got a wagon. All right, it's not a bad wagon for me. And then we've got this handle. What's the degree of the handle? 60 degrees. That's right. You doing physics next? Yeah, physics 2A. Okay. The person is pulling the wagon. My stick figure person is pulling the wagon. They're headed that way. All right. And there's an angle, an important angle here, of 60 degrees right there. This is what you always do in physics. Like I said, this weekend I did a ton of these with my daughter, and we have these angles everywhere, and we talked. And we're doing trig. It's a lot of trig, and we learned, is that the sine or the cosine of that angle? All the time. Trig in physics, all the time. There's angles everywhere, and you're doing sines and cosines. So, all right, so we're pulling that wagon straight to the right. The handle's at an angle of 60 degrees. Okay, now, and they want us to figure out how much work is done in pulling the wagon 70 feet. So that means that person goes 70 feet to the right, right? They pull that, and didn't it say level ground? Yeah. Level ground. That's important. Going up a hill is different. Those are hard when they do that to you in physics. They have you going up hills, and then you got to worry about the angle of the hill, and it gets really ugly. All right, so here we go. So the person is walking 70 feet to the right, pulling a wagon, handles at an angle of 60 degrees. How much work is done? Basically, we have 4 of these word problems. You know, there they are, 13, 14, 15, 16. All these problems, you basically have to just find the force vector, find the distance vector, and dot them. Then you got your answer. That's the whole problem. Find the force vector, find the distance vector. All right, so first off, let's start with the distance vector. That's the easy one. Distance is the movement. So how much does this wagon move?
70 feet.
Yeah, 70 feet. Now, to the right, up, straight to the right, huh? So the distance vector is going to be, think about I and J now. Is it going to be I or J? Or both? Just I, huh? 70 I. You could, just for extra completeness, you could plug in plus 0j if you want. That might help. You don't have to. You could just say 70i. That's fine. But you agree with me? The distance is 70 straight to, remember, right, left is I, up, down is j, huh? With the vectors. They're like x and y. They're just calling them I and j now. So straight to the right. So that wagon is going on level ground, so that means they're telling us no j. That's why they said level ground. It doesn't go up or down at all. If it was on a hill, you'd have to calculate all the angles and find the j component. So they're keeping it easy. So straight to the right, 70i plus 0j is the distance vector. We're halfway there. So we've got the distance vector. Now we just need to find the force vector, and then we'll dot them, and we'll have our work. That's the official definition of work. Okay, it's force over a distance. So, and that makes sense for work, right? That's what it is. All right, let's move on. How do we find the force vector? Well, force is the direction of your push and the amount. The amount and the magnitude and direction, vector, magnitude and direction of your push, right? So what direction is the person exerting force? They're exerting force right at that angle, aren't they? Not straight to the right. You with me? If they pulled that handle only straight to the right, the handle would come down to 0 degrees. Do you picture that? A lot of physics, you got to kind of feel it a little bit. Does that make sense? You feeling that? Right, you get the idea? So if you're pulling that wagon, and that handle's at the end, you're pulling straight on that handle. So probably my picture is not very good. I think my picture is deceiving. I don't mean to be deceiving, but I just realized it is. So let's put the person up here. I have trouble with pictures. So it's the best I can do. But they got this weird bendy hand there. They're like Plastic Man. Anyway, but they've got to be. I really should have made the thing taller, but I don't have time for it. Anyway, but my point is they're pulling in line with the handle. I should have made the pull in line with the handle, right? Really, I should have made it. Yeah, now it's bugging me. Because I want it needs to be real for you guys. I don't want it to just be something Mr. Heron says. I won't help you. So let me I made the wagon too high. So let me lower the wagon. Okay. So, and then the handle is at 60 degrees. Okay. And then the person's got to be a little bigger. Got to make a bigger person. So it's still weird looking. All right. So, boom. They're holding it right there. So they got a long neck, huh? It's just weird for you. I told you I got a C in art, right? In 7th grade. That was the end of my art career, and I was trying. All right. So Mr. Duran did not appreciate my artistic flair. He kept giving me C's on all my artwork. All right. That was before some of the more modern concepts that I could appeal to self-expression more. All right, anyway, so pulling. So my point is, the pull has to be in line with the handle, or the handle wouldn't stay at that angle, right? My other picture was deceiving because it looked like they were pulling straight on the handle. If so, the handle would come down, wouldn't it? And that'd be a different thing. So yeah, so their pull is right in line with the angle of the handle. That's what's keeping the handle at that angle, is that they're pulling at that angle, right? So do you feel that? So they're pulling at that angle. So their force is not flat. They're not pulling straight to the right, or that handle would come down straight. They're pulling at that angle, right? Because they're taller than the thing. So they're pulling the wagon at that 60-degree angle. That's the direction of their force. So now, the force is not exactly lined up with the distance, right? Their pull is up at 60 degrees. The movement of the wagon is straight to the right, which we've already done. Oops, I'm erasing it. We've already got that part. That's the 70i plus 0j. Anyway, all right, let's get it. So how do we do it from here? So we've got to figure out for this vector, this is the force vector right here. So what am I going to do?
Can we make a triangle?
Exactly. Good, Kevin. Come on down here. I'm going to make, this is the I component, and this is the j component, right? If they're pulling up to the right, then that's got a sideways component and a vertical component. Y'all see that? When they pull up when that person pulls up to the right at 60 degrees, so if I can, let me just blow up that triangle a little bit. Well, no, I'm going to leave it like it is. So that little triangle there, stick the 60 right in there. That little triangle, you make a right triangle. It's called the components of the force. So the force is at 60 degrees, but it has a sideways pull, the I component, and it has an up part. When you pull up to the right, that involves a sideways pull and a vertical pull put together, doesn't it? Get that idea? This is what physics does like all the time. This is just like everything physics does is they'll break, pull, and at some angle, some kind of force or work or distance or whatever, and they'll break it into what they call the components, the I component and the J component, the sideways and the vertical. So I'm saying, okay, the force is really at a diagonal, 60 degrees, but it's got a sideways component we call I and a vertical. How big are those? How am I going to figure out the I? The force itself is 40 pounds. Did you notice that? There it is, a force of 40 pounds. So they're pulling with 40 pounds, but that's in the diagonal direction, right? That's straight on the handle. They're pulling 40 pounds up to the right. So how much of a sideways pull does that end up producing, and how much of an up-down J pull is that? The 40 is broken up among sideways and vertical. How much for each? How do you figure that out? So if I give you a triangle, and I say this is 40, this is a right angle, this is 60 degrees, can you find the I and the J? That's what they're basically saying. How would we find I and J given a right triangle? So if we have a right triangle, what does that mean? We're going to use all the sine, cosine, tangent stuff we've learned, because that's all works for right triangles, doesn't it?
So the opposite angle is 30 degrees.
Yeah, the other's 30, but we don't even need it. Let's just start with this one. This side right here is this. This is what? Adjacent, right? And this is opposite. And this is hypotenuse. So what trig relationship, sine, cosine, or tangent, involves I and the 40? The adjacent and the hypotenuse. Cosine. Remember SOHCAHTOA, right? So SOHCAHTOA. SOHCAHTOA, yeah. So the cosine, let me come over here. The cosine of 60 degrees, I don't know what is wrong with my pen today. Cosine of 60 degrees equals adjacent over hypotenuse, I over 40. Doesn't it? Everybody see that? So how do I solve for I there? I'm trying to find I, right? What am I doing? I'm trying to find the I and the J components for my force vector. Multiply by the 40, huh? Yeah, exactly. Multiply by 40. Cancels out. 40 cosine 60 is the I. The I is 40 cosine 60. So I found the I component. How do I find the J component?
Sine?
Yeah, because that's opposite over hypotenuse, huh? The J is opposite the 60-degree angle. So if I do sine of 60 degrees, that'll be opposite J over the hypotenuse of 40. Is that good? Opposite over hypotenuse. And then how do you solve for J there? Same way, right? Just going to multiply both sides by 40. Cancels. So the J component is 40 sine 60. So we got the I and we got the J. Hey, is it any surprise at all that the sideways I component, the X, ends up having the cosine? We've seen that all semester long, huh? Cosine is always the X. Remember when we do the unit circle? Did it just a minute ago. What did I do right here? Somewhere. Where is it? Have we done that much work? There. Cosine is X. Sine is Y, right? That's what we've always learned all the way through, and that is still the case, always will be. So basically it makes sense that the I component ends up having the cosine and the J component ends up having the sine, right? All right, so with all that, what does all this mean? We've now got the force vector. The force vector then, which is 40 cosine of 60 degrees I plus 40 sine of 60 degrees J. Right, that was the I and the J we got here. I and J for the force vector. And the distance vector, what was that? It was 70I plus 0J.
How many decimals does it want?
I have no idea. All right, and we will dot this. We're going to take force dot distance. Remember, because that's work. Work is defined as force dotted with distance. How do we do the dot product? We just multiply the I with the I and the J with the J, and we drop the I's and J's, don't we? So just multiply this with this. Use your calculator. So it's just 40 cosine 60 times 70. Make sure you're in degree mode. Oh, I'm getting 1400 straight plus 0. So 1400. What are the units? Foot-pounds. Foot-pounds of work. We good there?
Is that because the number is times, because the 0J is times the other J?
Yeah, the 0 times this is 0. We good there? The I times the I and the J times the J. 1400 foot-pounds of work. Questions on that one? No, yeah.
No, we do not, nothing with the, oh, right, never mind. Okay.
That good? So it's all about finding the force vector and finding the distance vector. And they're both vectors. They both have I and J. So the distance vector was straight to the right, 70, so that was 70I. The force vector was 40 pounds at an angle of 60 degrees. So I'm not going to go through all this work, and I don't want you to have to either from now on. Anytime because this will be very common, we'll have a force at an angle, like whatever, like 40 pounds at 60 degrees. It'll always just be that number times cosine of the angle for I times sine of the angle for J. Because cosine is always sideways, sine is always vertical. You do a ton of that in physics. I was doing it this last week with my daughter. It's exactly what always happens. All right. We good? Let's try. Okay. A force of 80 pounds on a rope is used to pull a box up a ramp inclined at 10 degrees from the horizontal. The figure shows that the rope forms an angle of 33 degrees with the horizontal. How much work is done pulling the box 21 feet along the ramp? So whenever they ask how much work, what are we going to do? Force dot distance. So it's all about finding a force vector and finding a distance vector, and then just do the dot product, and you got your answer. So we got to find a force vector. We've got to find a distance vector. So let me let you try that. So they both have an angle, don't they? So to get the idea, so let's do the force first off. The force is 80 pounds at an angle of 33 degrees. So it's going to be just like the last one was. Which means it's going to be 80 cosine 33I plus 80 sine 33J. Does that make sense? So the force vector is 80 cosine 33I plus 80 sine 33J. See what I'm doing there? Because there's a force of 80 pounds at an angle of 33 degrees. And then they call that an angle with the horizontal, right? Because it's above flat. So there's the force vector. That's half the battle. Now get the distance vector, the movement vector. How does that box slide up the ramp? Well, it's sliding at 10 degrees, isn't it? So yeah, the movement is a little bit different angle than the force, just like the last problem we did with the wagon. So the movement is at 10 degrees. How far does it move? 21 feet. So in other words, this box moves from here to there, 21 feet at a 10-degree angle. So what's the distance vector going to be? Same thing as the force. 21 cosine 10 degrees I plus 21 sine 10 degrees J. Making sense? See how we're doing that? See how it's kind of the same thing every time like that? Bless you. And now we just dot them. Work is force dot distance, which means you take the I times the I, drop the I's, right? Just use your calculator. 80 cosine 33 times 21 cosine 10. I'll do that too. See what we get here. 80 cosine 33 times 10. Just do it all in one big thing. Times 21, I mean. 21 cosine 10. I'm getting 1387. How many play? They want nearest foot pound. 1387 point, I'll just go 56 plus, and then you do the J with the J and drop the J's. 80 sine 33 times 21 sine 10. I'm getting 158.89. Add those together. I'm going to use the answer key on my calculator. Just add the last answer. Whoops, I made a mistake. I'm getting 1546.45. So it'll round to 1546 foot-pounds. Foot-pounds of work. Is that working out okay for you? Questions I can answer? All good? No questions? So you just, whenever there's a force or a distance at an angle, it's all the same. It's just whatever the force is, 80 pounds, or whatever the distance is, 21, times cosine of the angle I, sine of the angle J. Because cosine is X, sine is Y. We've seen that all the way through the semester. See how all these things tie together? That's what all this is for real life problems like this. That's what all this math was made up to do. Yeah.
See your work for the sine portions of
I just typed into my calculator.
yeah.
Yeah, so I could check with your calculator. It was just all calculator. Just multiplied it. That was just all multiplied together on my calculator. Just these guys right here. On that. So grab, if you're having trouble getting those on your calculator, glad to help. Grab me after. Find the work done. Okay. So they're asking for work. You know the deal. We need the force vector and the distance vector. The force vector, they're just handing us the force vector. But what about, how are we going to find the distance vector? What are we going to do to find the distance vector there? Yeah, I would just, yeah, so let's just put these on an axis system. That's what they're talking about, huh? So back 6, 1, 2, 3, 4, 5, 6, up 2 right there, and then 1, 2, 3, 1, 2, 3 right there. So there's 3, 3. There's back 6 up 2. And there's the distance vector. You with me? I'll call it capital D. That's the distance vector right there. It goes from negative 6, 2 to 3, 3. That's how they're moving some object. So I've got to make that a vector. I've got to make that movement a vector, which means it needs an I and a j. How am I going to find the I and the j for that distance vector? Let me give you a second, rather than me just whip it. So the distance vector is going to be what? How about I call this x1, y1, x2, y2? Do you see what it's going to be? x2 minus x1 I plus y2 minus y1 j. You know what I mean? If I want to know, because really the vector has a certain amount of sideways, that's the I, and a certain amount of up, this is the I, this is the j. With me, it's got an I and a j. So it goes from negative 6 to over 3. This is x2, this is x1, huh? So if you subtract those, you get the I. And then if you subtract the heights, you get the j, don't you? See how it's a difference of x is I, difference of y is j? It's a slope, basically. It's kind of like a slope. This is the rise, the j. This is the run, the I. Run is sideways, huh? Does that make sense, how I'm doing that? So then the distance vector is going to be, I already wrote them up there, didn't I? So it's going to be x2 minus x1, 3 minus minus 6, which is what? 9 to the right. And the y's are 3 minus 2, which is 1j. So it's 9 to the right, up 1. Yeah, that vector, that distance vector goes 9 to the right and up 1, doesn't it? See how we figured that out? So now just take your force vector, your distance vector, and dot them. And you got your work. So I'll do it over here, I guess. So work is force vector dot distance. So I've got the 7i, let's write it here, 7i plus 4j, and I've got the 9i plus 1j, and I'm doing the dot, let's write it like that, dot product, 7 times 9, 63, 4 times 1, 4, drop the i's and the j's, right? Dot product means multiply I with I, j with j, drop the i's and the j's, 67, 67 what? Yeah. Yeah, foot-pounds again. My old physics, they always want the units. That's important. I remember my first physics teacher back in my high school days, Mr. Grimes. If you ever gave an answer like 67, he'd go, 67? 67 what, Heron? 67 dogs? 67 dogs in the kennel? That was always his response if you didn't give the units. So physics cares about the units. Like, what are those? I'm a math teacher. I just want the number. Just give me the number. I'm happy with 67. But physics, they're trying to be real. What is that? 67 foot-pounds of work. There we go. Not 67 dogs. We good? Everything good there? Questions on that? So a force of 3 pounds. You probably can't even read that. Yeah, let me rewrite this one. So right here, number 16. Force 3 pounds at 46 degrees to the horizontal. It moves some object from 2,7 to 7,8. Find the work. So you know the deal. Find the force vector, find the distance vector, do the dot product. So give you a second, see if you can find both. Okay, you guys getting the, so let's start with the force vector. How you all doing? You getting the force vector? It's 3 pounds at 46 degrees. So what does that mean we do?
3 cosine 46.
Beautiful. 3 cosine 46i, because cosine is always sideways, plus 3
Sine 46.
46j. Good? For the force vector? And now, let's get the distance vector. So the distance vector. So how are we going to do it when you move a couple points? You remember, it's the difference in x is I, because x is the sideways I, plus the difference in y's, because that's like rise, j. So the distance vector will be, so this is x1, y1, x2, y2. It's going to be 8 minus 7i. Oh, wait, that was I did the wrong ones. That was let's try it again. 7 minus 2i and 8 minus 7j. So what is that? That's 5i plus 1j or j, yeah. Good, we got the distance vector. We got the force vector. Dot them. Use your calculator. So the work,
And this is hundredths this time.
ooh, they want 2 places, 2 decimal places. So the force vector dotted with the distance. So I'm going to multiply the I times the I. So what's that going to be? I'm getting 10 point. So I'm going to go. Remember, when you're in the middle of the problem, you want to use more accuracy than you need in the end. So I'm going to use like 4 places for now or whatever. 4.198 plus, and then the j component 3. So, and I'm getting 2.1580. I'm getting 12.577, so that'll round to 12.58 foot-pounds. Good there? You guys getting that okay? Foot-pounds. My physics teacher would not be happy with me here. Foot-pounds, there we go.